We as independent observers come across objects moving in straight lines in our day-to-day lives. With our busy schedules, sometimes we won't be able to observe the physics behind this simple phenomenon. Before we jump into our main topic, we shall discuss one of the most important segments in mathematics, vectors. The textbook definition of a vector is an element in a vector space with a magnitude and a direction. Now that we know a bit about vectors, we shall discuss the main topic at hand. First, let's define the terms involved with linear motion. Distance, the total length between the initial and the final point of motion. Displacement, the shortest length between the initial and the final point of motion. Speed, the rate of change of distance. Velocity, the rate of change of displacement. And acceleration, the rate of change of velocity. Behind the physics of linear motion, we find the three equations. These equations are called kinematic equations of linear motion. We shall look into the following cases to unravel what these equations are. Consider case 1. An object starting its motion at an initial velocity of u and moving with a uniform acceleration a over a time period of t. If the final velocity of this object is v, then by the definition of acceleration, which is acceleration is equal to the difference in final and the initial velocities over time, we get that a is equal to v minus u over t. By cross-multiplying and subjecting final velocity, we derive our first kinematic equation, which is v is equal to u plus at. Case 2. Consider an object starting its motion at initial velocity u and moving at a uniform acceleration of a for a time t. Say it displaces a magnitude of s until its final velocity is v. There is a theory where we measure the displacement using average velocity. By the definition of velocity, it is equal to the rate of change of displacement here, that is s over t, but the s over t gives a specific value which doesn't change with time. In other words, it gives the magnitude of uniform velocity. So, it's a contradiction, since in this case the object is accelerating, changing the velocity with time. Therefore, average velocity is taken into account. In this case, average velocity is equal to u plus v over 2. Now, this value coincides with the value we get for s over t. Therefore, u plus v over 2 is equal to s over t. By case 1, substituting v is equal to u plus at and cross-multiplying with t, we get s is equal to 2u plus at times t over 2. Simplifying this, we have s is equal to ut plus half at squared, which is the second kinematic equation. Case 3. Consider an object starting its motion at velocity u and moving for a time t under a uniform acceleration a. If it displaces by a magnitude s, by the definition of acceleration, which is a is equal to v minus u over t, we can subject t, where t is equal to v minus u over a. By this equation, s is equal to u plus v times t over 2, and substituting the above value for t and simplifying, we get the equation s is equal to v squared minus u squared over 2a. By cross-multiplying and further simplifying, we get final velocity squared equals to the sum of the initial velocity squared and 2 times acceleration into displacement, which is v squared is equal to u squared plus 2as. This is the third kinematic equation. These are the three equations that we should know to deal with any problem involving linear motion with uniform acceleration. The three kinematic equations are v is equal to u plus at, s is equal to ut plus half at squared, v squared is equal to u squared plus 2as. Now, the most important thing that we need to remember is that these equations can only be used in cases where the acceleration is uniform throughout the motion, which means these theories prove to be wrong when dealing with simple harmonic motions. Now that we have arrived at the end of our episode, we will leave you with this problem. If a point moving under uniform acceleration describes successive equal distances in times t1, t2 and t3. Then prove that 1 over t1 minus 1 over t2 plus 1 over t3 is equal to 3 over t1 plus t2 plus t3. This question is taken from SL Loney's Dynamics. You may pause the video and write it down. Along with the proof, we shall meet you in the next episode where we discuss graphs of motion. Until then, goodbye.